Hi everybody. This video will cover section 1 of chapter 2, and in this video we will discuss frequency distributions. Specifically, we will talk about how to interpret a frequency distribution, the characteristics of a frequency distribution, and then we will introduce two special types of frequency distributions. One is the relative frequency distribution, and the other one is the cumulative frequency distribution. Okay, so for a little bit of motivation, let's just pretend that we are a scout for a Major League Baseball team. And the Major League Draft is coming up, and we want to, for our very first draft pick, find the best player that will fit the needs of our team. And one of the statistics that we're going to look at is this statistic called on-base percentage. And basically, the on-base percentage is, well, for a given for a given appearance at the plate, what's the probability or the percentage that you will actually get on base, either via a hit, a walk, being hit by a pitch, a balk, or whatever. And it turns out that in the 2022 season, there were 2,063 Division I baseball players, and these are the on-base percentages for probably a little less than half of them. We actually have 850 data points on this screen. So there's our number. There's our data. Now, clearly, if you look at this, all I see is a bunch of numbers. It does not give me any idea of how they're distributed, which one, where data is concentrated, what are the outliers are. We know that the numbers can be as high as 506, or the numbers can be as low as, let me see, I found a 352 here. And once again, this is only less than half the data. Imagine trying to see all the other data sets. So looking at the data by itself is of no value whatsoever. However, if you look at it in terms of a frequency distribution, it makes more sense. Now what is a frequency distribution? It is a table that tells how often the values of a data set occur. Okay, and for example, if, it turns out that there is one value or one data element, or we have one player whose on-base percentage is greater than is between 550 and 559. And we can tell that the largest concentration of on-base percentages is right about here. Okay, notice that this table has two different columns. The first column is the class, and this is basically does nothing more than subdivide all the possible values for on-base percentage. And the second one is frequency. That's how many data sets or data values are in that particular range. So you can look at this and you can get a good idea of where the major concentration of data are, where the outliers happen to be, and get a good idea of who you actually might want to draft. You might want to draft one of these 17 people depending upon what the other statistics look like. Okay, and as I mentioned before, it allows us to visualize the structure of our data set. Okay, as I mentioned before, the basic frequency distribution has two columns. One is class, which provides you the category of the data, which in this case is the range of data values for a given class. And here we have the frequency, which tells you the number of data values for each category. So this range is a category, this range is a category, and so forth. Okay, taking a look at class, notice that we can break the range in classes into a lower class limit and an upper class limit. So this is the lowest value associated with the class. This is the largest value associated with the first class. This would be the lowest value associated with the second class, the largest value associated with the second class, and there are 66 data elements or data values that fall within that category. And of course, and similarly, the lowest value, largest value, one element. Now, perhaps the most important and useful parameter in interpreting frequency distributions is the class width. There are many ways to define it. In this particular case, we are going to define the class width as the difference between the lower class limits of two adjacent classes, and the class width is always a positive number. For example, class 1 and class 2, adjacent classes. The lower class limit for class 2 is 250, the lower limit for class 1 is 200. Class width is 50. Okay? Notice that you can take any two adjacent classes and you'll get the exact same number. You can take any two adjacent classes and compute the difference of the upper class limit, the exact same number. So the biggest thing to point out, however, is this. We need to use the lower class limits of adjacent classes. The class width is not 249 minus 200. It is not 49. It is 50. And the reason why we use this as a class width will become very prevalent when we talk about a few other things. The next thing we need to talk about is the class boundary. Even though this is the upper limit for the first class and this is the lower limit for the second class, the class boundary is that point that separates the two classes. Notice we have this little region here which we could probably call purgatory. I was trying to think of the appropriate word, but purgatory is the one that I want, where there should be no data values, but nonetheless we want to have one value which basically serves as a boundary, and this will be the boundary. It is the value that lies halfway between the upper limit of one class and the lower limit of the next or adjacent class. Okay? For example, here's class 1, here's class 2. The upper limit is 249, the lower limit is 250. As a consequence, the upper class boundary for class 1 is going to be the average of those two numbers, 249 plus 250 divided by 2, 249.5. Don't even need to do that kind of math. Look, here we have 249, here we have 250, number in the middle, 249.5. Notice that this is the upper class limit, upper class boundary for the first class, and it's also the lower class boundary for the second class. Okay? Now, the question here is, what is the lower class boundary for the first class? Notice there's no number here to take the average of. Not a problem. The difference between class boundaries is going to be some multiple of the class width. So if this is 249.5, we can take the 249.5, subtract 50 from it, and we will find the lower class boundary for class 1. Similarly, we could take 249.5, add 52, add the class width to that, and we will find the upper class boundary for the second class, which will be 299.5. And you will notice that I do indeed have a typo on this particular slide, which I thought I got rid of. Apparently I didn't. The upper class limit for the second class is not 399, it is 299. The class boundary, the upper class boundary for the second class, that's a pretty poor line, is 249.5. Okay, does that kind of make sense? Well, yeah, because remember, this plus the class width will give us 249.5. 299.5, sorry, my bad, 299.5. And also notice that the lower class boundary, or the lower class limit for class 3 is 300. What's the average? 299.5. Sorry about the lousy handwriting there. The next thing, the next value that we care about is the class midpoint. Class midpoint is relatively straightforward. It is going to be the number in the middle for any single class. How do you find the number in the middle? Take the average. In this case, it is going to be 200, the lower class limit for class 1, plus 249, which will give us 449, divided by 2, and that will be 224.5. Okay, now once you have found the class midpoint for one class, you can find the class midpoint for all the other classes by adding to this the class width. Class width is 50, so the next midpoint is going to be 274.5 for class 2, and then that's supposed to be a 4. There we go. That's a little better. And of course, class 3, it will be 324.5 and so on. So you actually have two ways to compute this. If you already know one midpoint, the other midpoints are going to be a multiple of the class width, or once again, it's just the average between the lower limit and the upper limit for a particular class. So if you put all this together, you would have this particular table. Notice here we have our two original columns, class and frequency. These are the class boundaries. Okay, we actually computed this, and then we can actually subtract 50 to get the lower class boundary. Remember, we share class boundaries here. Add 50, the upper class boundary, add 50. Notice that all of these have a difference of 50, the class width. Similarly, all of these also have a difference of 50, once again, the class width. So that is why the class width is very important. And that is also why it is computed as the difference of the lower class limit of the two classes. Okay, now we're going to talk about the two specialized frequency distributions that I mentioned earlier. The first one is the relative frequency distribution, where instead of computing the frequency, we compute the relative frequency. Now, the relative frequency is going to be the fraction or percentage of the data that falls in a given class. Specifically, it's going to be equal to the frequency of that class divided by the total number of data sets. Now, notice that the total number of data sets is going to be the sum of all of these values. Okay, if you add all these up, you will have n. Okay? So in this particular case, the relative frequency for the first data set is going to be 3 divided by n, which actually happens to be 2063. Okay. Now, when you compute all the relative frequencies, that should be RF1, I suppose, and if you sum them up, they will always be equal to 1 if they're a decimal or a fraction, or 100% if it is a percentage. So here we have a relative frequency distribution. It contains the class, it contains the frequency, although it does not have to, and it contains the relative frequency, which in this case are fractions. Now, one of the things you have to be careful about when you compute these is that the fraction must be a reduced fraction, i.e. the numerator and the denominator cannot have common factors. Okay? If you do, they need to be factored out. Fortunately, 2063 happens to be a prime number. Okay, so as a consequence, all of these are reduced fractions, so we don't need to worry about it in this. We don't need to worry about reducing in this particular case. The next frequency distribution is called a cumulative frequency distribution. And before we can do that, we need to talk about what a cumulative frequency is. And it is the sum of all the frequencies of a given class and all previous classes. So what we can do is just come over here and take a look at class. Let's go back to this one, works better. No, one more. There we go, to class 1. So here we have class frequency. Your cumulative frequency works as follows. Okay, remember the cumulative frequency is going to be is going to be equal to the frequency of the class plus the frequency of the sum of all the frequencies of the lower classes. Since this is the lowest class, the cumulative frequency is 3. Here, the cumulative frequency for the second class is going to be equal to 66 plus the frequency of the one lower class, which will be 3, which will give us 69. For the third class, we will have 381 plus 66 plus 3, or 381 plus 69, which will give us 450. For the fourth class, we will have 450 plus 860, which will be 1310, and so on. And if we compute all these, we will have our cumulative frequency distribution, which is what we actually have here. Notice that the cumulative frequency of the last class, the highest class, class 8, is actually equal to the number of data points in the data set. This will always be equal to n, where once again, n is the number of data items in the data set. And the last thing that we want to talk about today is the idea of an ordered array. An ordered array is just simply nothing more than a sorted array. Now, how can you do this? Well, you can do this by hand or you can make use of your TI-84 calculator. And what I have here is a computer emulation of that calculator. There we go. That's actually where I wanted it. Okay, so how could you do this? Well, the first thing you need to do is you need to enter the data. Okay, and the way that you can do that is go into Stat right there, and we want to go to Edit, and these L1, L2, L3, L4, these are lists of data, and we want to enter in the data items into L1. So that's what we're going to do here. Notice that L1 is 111, or that the first data item is 111. Okay, next we have 94, 57, 80. Let's move this out of the way a little bit. Okay, 78, 109. We can go to the other side. 92, 34, 67, 122. Okay, that should be 10 items. Let's just make sure that they are correct. 111, 94, 57, 80, 78, 109, 92, 34, 67, 122. Okay, once you've done that, we need to exit. And that will be second mode to quit. Go back into Stat, and notice here we have sort ascending, which is what we want to do here. So to do that, so you just want to go down there, click that, and now we need to select L1. That was the list where we had all that data in here. And over here in blue is lists. So if we do second Stat, we have all the lists. We want to select L1, so we can either hit 1 or enter, close the parenthesis, and hit enter. And it tells us that it is done. Oh great, how can we make sure? What we can do is go into Stat and Edit, and now look at L1. Notice that it is all sorted. And also notice that that the sorted values are consistent with what we have here. 34, 57, 67, 78, 80, 92, 94, 109, 111, 122. So this provides a convenient way to sort data, which actually makes it a lot easier to come up with the frequency values for frequency distributions, which is a homework problem. And this is something you want to get used to, because this is a tool that you can actually use when you are taking an exam. And that is all that I have for this particular video. If you have any questions, please feel free to contact me. Please stay tuned for a follow-on video where, yes, I do your homework for you. And until then, this is Bob Boyle.